Hi everyone. So as I mentioned before, the remainder of this class, we're going to be focusing on specific important types of functions. And so the next type of function we're going to be focusing on is a function called a polynomial. So we'll be spending a few videos talking about polynomials. This is the first video where we'll be introducing what a polynomial is, and then also talking about a specific feature of actually all functions, but we'll be talking about it within the context of polynomials, and that's called end behavior. Okay, so what is a polynomial? So a polynomial is a function of the form. So I just want to pause for a moment and tell you that what I'm about to write down is going to look a little bit complicated. Bear with me. We'll see that it really is not as complicated as it looks. It's just kind of the way that you have to write down the definition of a polynomial. Once we see some examples, I think you'll see that it's really nothing as scary as it looks. So I'm just going to write this down, and then once I have everything written down, I'll explain what I mean by all of this. Oops, I forgot an x. So in this expression, or in this function, these numbers here, an minus 1, a1, a0, those are just numbers. So I'll write that down. Oops, here. an minus 1, a1, a0 are real numbers. And n, so n being this number here, is a positive whole number. Okay, so why does this look so crazy? Why is there so much going on with all these different letters and numbers? Well, basically, what is a polynomial? A polynomial is a function where you're adding up or subtracting different powers of x multiplied by different numbers. And so the reason that this kind of format looks so funny is because we want to write down the most general expression we can. And a polynomial can include any power of x, as long as that power is a positive whole number. And so that's why we use n here. N represents whatever the highest power in that polynomial is. And so we have to use n to be as general as possible, right? We don't want to say, oh, it has to be x to the 5th or x to the 10th or x squared. It can be any power of x. And so why do we have to do these funny like an minus 1? Well, it's because, again, we're being very general and we don't know how many different powers of x there are, right? So just to remind you, for quadratic functions, those we wrote down, right, as ax squared plus bx plus c, right? So we use these letters a, b, and c to represent the numbers that were being multiplied with the different powers of x. We can't do the same thing here because, again, we don't know how many powers of x we have, right? So we could say a, b, c, d, e, f, g, but like we just don't know how many powers of x we're talking about because we're writing down this very general formula. Okay, so let's look at some examples of what a polynomial could look like. And then I'll come back. There's a little bit more I want to add here. So if you're taking notes, you might want to leave a little bit of space. I just think it's better to jump into a few examples before we get into like the more kind of technical details. So one example of a polynomial would be f of x is equal to negative 3x to the 4th plus 5x squared minus 2x plus 1. So that is a polynomial, just adding up different powers of x. Notice that you don't need to have every power of x, right? So it's okay to have x to the 4th and then jump straight to x squared. Just like with quadratic functions, remember you don't need to have an x squared and an x and a plain number. You know, there's different possibilities. Another example of a polynomial would be x to the 10th plus 5. That is also a polynomial. Another example of a polynomial would be 1/2 x squared plus 3x minus 7. So this might look familiar, right? So what I just wrote down, that is actually a quadratic function. So it turns out that quadratic functions are just a special type of polynomial. So polynomial is like the more general category, and quadratic functions are a specific type of polynomial. Similarly, you could also have a linear function. So 5x plus 1, that is a polynomial. So as long as all you're doing is adding up different powers of x, you're good. It's called a polynomial. What would be an example of something that is not a polynomial? Well, let's say you had something like this, 3x squared minus x, but then that was divided by x cubed plus 5. So why is this not a polynomial? Well, it just doesn't fit this format, right? The format, it's supposed to just be that you're adding up these different powers of x multiplied with different numbers. Here you are doing that in the numerator, but you're also doing it in the denominator. So this is actually called a rational function, and that's a different type of function that we'll get to later. So this is not a polynomial. Another example of something that would not be a polynomial would be if you had something that maybe initially looked like a polynomial. So it's like 3x cubed minus 2x squared. But then as soon as you tack on something where the power of x is not a whole number, a positive whole number, right? So square root of x would be x to the 1/2. That's no longer a polynomial. So it really just needs to be positive whole number powers of x. Okay, so those are not polynomials. So let's get back to defining a little bit of vocabulary that we're going to need to know as we discuss polynomials. So the first piece of vocabulary is a name for these numbers here. So these numbers that you're multiplying the different powers of x with, as well as this number at the end that is just kind of a number on its own. So these numbers, actually, sorry, I need to give myself a little more space. an minus 1, ... down to whatever these last numbers are. These are called coefficients. So that's a word that I'm guessing most of you have seen before. I've probably used it here and there in the class. So coefficients are basically just numbers that are being multiplied with some kind of an expression. So in this case, we're talking about coefficients as the numbers being multiplied with the different powers of x. There's a special name for the highest one. So whatever your highest power of x is, the number that's being multiplied with that highest power of x, that is called the leading coefficient. And so that's something that we will be using later on in this video. Now, if instead of talking about the like just the numbers being multiplied with these powers of x, if you want to instead refer to the entire kind of piece that's being added up, those are called terms. So an x to the n, an minus 1 x to the n minus 1, a1x, and a0, those are called terms. And again, that's a word that I'm going to guess that you've seen before. Terms are basically just within an expression, the different pieces that you're adding up. Those are called terms. One thing you might notice that may seem a little weird is that we listed a0 in both places, right? We said a0 is a coefficient. We also said a0 is a term. It's just because it's not really being multiplied with any power of x, but technically you could think of it as being multiplied with x to the 0, right? Because x to the 0 is equal to 1. So that's why it can technically be considered a coefficient. It can also be called a term. It doesn't really matter. It's not really something to worry about. So usually what we call that last number that is being, the number that's on its own, that is usually referred to as the constant term. You could also call it the constant coefficient if you want. I'll probably call it the constant term in this class, but it doesn't really matter that much. And then the last thing that I want to point out here is the highest power of x. So whatever that highest power of x is, that is called the degree of the polynomial. And that's probably, of all of these things, that's probably the most important word of all of these. So whenever we're talking about the degree of a polynomial, we're talking about specifically the highest power of x that appears in that polynomial. Okay, so I just want to quickly go through these and identify, for the ones that are polynomials, I want to identify their leading coefficient and their degree. So this might be a good place to pause the video and try this yourself just to make sure that you understood what these words mean. So the leading coefficient and the degree. So remember, the leading coefficient is just the number that's being multiplied with the highest power of x. So in this case, the leading coefficient is 3. Or sorry, -3. And then what is the degree? Well, the degree is just whatever the highest power of x is. And so in this case, we would say the degree is 4. Okay, what about this next one? So in this case, we don't really see a number being multiplied with x to the 10th. However, we can say that the leading coefficient in that case would be 1, right? Because if you really wanted to, you could write this as 1 times x to the 10th. And then what is the degree? Well, again, the degree is just whatever that highest power of x is. So in this case, the degree is 10. Okay, next up we have this quadratic polynomial. And so in this case, our leading coefficient is the number that we're multiplying with x squared, so that's going to be 1/2. And then what is the degree? Well, the degree is 2. And so as we mentioned earlier, there's a special name for polynomials of degree 2. They're called quadratic functions. So basically, quadratic function and degree 2 polynomial, those just mean the exact same thing. What about our last one? So our leading coefficient. So in this case, what's the highest power of x we have? Well, we just have x. And so our leading coefficient is going to be 5. And then what about the degree? So in this case, we don't really see x being raised to a number, but if you just have x, that's the same as x to the first power, right? I'll just put that in there. And so the degree is going to be 1. And so similarly to what we said on the last one, whenever you have a degree 1 polynomial, well, that's the same thing as a linear function. And by the way, there are special names. So if you have a degree 3 polynomial, that's sometimes referred to as a cubic function. If you have a degree 4 polynomial, that's referred to as a quartic function. And there are names as you go higher and higher, quintic, etc. But for the most case, I'd say people usually talk about linear, quadratic, cubic, maybe quartic, and past that, most people would just say degree 5, degree 6, etc. Okay, so now that we know what polynomials are, we're ready to talk about a specific feature of functions, which we'll be talking about in the context of polynomials, which is something called end behavior. So this, you'll see, I think, is a topic that might feel a little different from other things we've talked about in this class. It might feel a little bit more kind of wishy-washy or sort of approximate. We're not going to be talking about like specific numbers or being very specific. We're going to be talking about general trends in this section. And this is something that you'll actually get a lot more into when you get into Calculus 1, this idea of kind of trends of where a function is heading. Okay, so what is end behavior? The end behavior of a function is a description of what happens to the outputs of the function as, and I'm leaving a little space here because I'm going to kind of add something between these lines later, as x gets very large or very small. So we'll get into some examples in a moment, but I just want to say one thing just to get it out of the way up front. When we're talking about x getting very large or very small, so when we're talking about x getting very large, we're talking about things like x equals 100, x equals 1,000, x equals 1,000,000, right? We're basically trying to assess what is going on with the outputs of this function as we plug in bigger and bigger x values. What about as x gets very small? What do I mean by that? So this is the one that I think sometimes can be misleading. Like when you hear very small, personally, when I hear very small, the first thing that pops into my mind would be a number like 0.1, right? That seems like a very small number. But when I say very small in this video and in this topic in general, I'm actually talking about numbers that are very far to the left on the number line. So that would be numbers like -100, -1,000, -1,000,000. So just be sure that when we're talking about very small, that's what you have in mind. I'm not talking about like teeny tiny numbers that are close to 0. I'm talking about numbers that are very far to the left on the number line. So very large means very far to the right on the number line. Very small means very left on the number line. Okay, so the way that we're going to start by doing this is just by looking at a graph and basically using the graph to tell us what the trend is, where this function is heading. So right here I have graphed the function f of x is equal to -2x to the fourth plus 3x squared plus 2x minus 1. So this is a polynomial, right? And by the way, like the main thing that we'll be discussing over the next few videos is what the graphs of polynomials look like and identifying different features of those graphs. So here is the graph of this polynomial. I'm just going to put these kind of arrows at the bottom to emphasize what's going on here. So what I want to do is describe what is the trend? Where are the outputs of this function heading? So as x gets very large, what is happening to f of x? So as you're, and we can't see the whole graph here, but I want to just think about the trend. Like as we're going further and further to the right on the x values, what are happening to the y values of this function? What are happening to outputs? Well, they're going down, right? The bigger the number you plug in for x, the smaller your output is going to be. And again, it's even like we can see it's going down so steeply that we can't even see a big value of x here, right? It would just be off of the graph because this graph is so steep. So what we can see is that as x gets very large, f of x gets very small. So another way that you can kind of think about end behavior, other than the definition that I wrote up at the top, kind of the reason it's called end behavior, you can think of it as a description of like, how are the ends of your graph pointing, right? If you think of these points down here as like the ends of your graph, it's like, where are they going? And we can see that to the right, the graph is pointing down. So the end is going to negative infinity. What about as x gets very small? So that would mean now looking to the left. So as you plug in numbers that are further and further this way, what is the trend of where the function is heading? Well, it's also going down, right? Both ends are pointing down. And so as x gets very small, f of x also gets very small. So that's kind of a description in words. It turns out we're going to be using a special notation for this description of end behavior. So from here on out, we're going to be writing down sentences like this the following way. So instead of saying as x gets very large, the way we're going to write it is as x, and then we put this little arrow, and then we say infinity. So as x, you can read this as x approaches infinity. So as x gets bigger and bigger, as x trends towards infinity. And so what should we say for f of x? So if f of x is getting very small, that means that f of x is trending towards negative infinity. So I'm going to put this in a box because this is really the way that we want to be describing end behavior. So similarly here, what can we say? Well, as x gets very small, that would mean as x approaches negative infinity, right? As x trends towards negative infinity, well, then we see that f of x is also trending towards negative infinity. And so if this was like a quiz or a test or a homework question where I was asking you to describe the end behavior, your answer would be the stuff that's written in these boxes. So I just want to add that to our kind of definition up here. I don't know why my screen is freezing. So when we talk about x getting very large, that we describe as x approaches infinity. And when we talk about x getting very small, that would be x approaches negative infinity. And then when we talk about what happens to the outputs, well, that's either going to be f of x approaches infinity or f of x approaches negative infinity. It depends on what your graph looks like. Okay, so let's look at another example. And then basically what we're going to see is that it turns out that there are some rules where without having this graph in hand, the goal of this video will be to be able to see a function like this and figure out what its end behavior is without looking at the graph. And so that will help us in the future when we're actually trying to sketch the graphs of these functions from scratch. Okay, so next example, this one I didn't write down. Let's see, this is f of x is equal to, or I'll call it g of x, is equal to 3x to the fifth minus 2x squared plus 1. So I would encourage you to pause the video at this point and try to describe this end behavior yourself using the same kind of format that we did on the previous question. And I'm just going to throw on these little arrows here to remind us of what's going on with this function. Okay, so how would we describe the end behavior? So first thing you need to know is that describing the end behavior is always going to start like this. You're going to have as x approaches infinity, f of x approaches something, and then you're also going to have as x approaches negative infinity, f of x approaches something. So really the only thing we're trying to figure out is what goes here and here. Okay, so let's talk about first as x approaches infinity. So in this case, we're talking about as we plug in bigger and bigger numbers, as x gets bigger, what's happening to the outputs? Well, in this case, we can tell that the outputs are going up, right? And so as x gets larger and larger, f of x also gets larger and larger. Similarly, if we look at going in the negative direction, so now we're plugging in smaller and smaller numbers for x, well, what's happening to the outputs of the function? They're going down. And so as x approaches negative infinity, f of x also approaches negative infinity. So that would be our description of the end behavior. Okay, so it turns out that in order to understand or identify the end behavior of any polynomial, you really only need to be familiar with the end behavior of 4 very simple polynomials. So let me just kind of title this as the end behavior of 4 simple, and I'll say, but important polynomials. So again, a polynomial can be anything that is powers of x, and so that includes just functions like x squared, x cubed, negative x squared, negative x cubed. Those are all polynomials. They're very simple polynomials, but they are considered polynomials. So what I want to do is sketch the general shape of each of these graphs and talk about what their end behavior is and like why it is the way it is. And then we'll make a connection between the earlier examples we looked at and these 4 examples. Okay, let's start with f of x is equal to x squared. So what does that look like? Well, hopefully you know that this is a parabola. Okay, so how would we describe the end behavior for this function? Well, we would say as x approaches positive infinity, and maybe let me do it as, I'll do negative infinity first. It doesn't matter what order, but it seems like it makes a little more sense to go from left to right. Okay, so what is going on? As x approaches negative infinity, where is f of x going? As x approaches negative infinity, that means we're looking at plugging in x values further and further to the left on the number line. And we can see that our outputs are getting bigger and bigger, right? The further you go left, the higher and higher the outputs are. And so as x approaches negative infinity, f of x approaches infinity. Similarly, if we plug in a value further to the right, so if we go further and further to the right, what's happening to the outputs? Well, the outputs are still going upward. So as x approaches infinity, f of x also approaches infinity. So before we move on to the next one, I want to talk about why is that? Like, why is that the end behavior for this function? Well, it basically has to do with the fact that we are squaring it, right? So one kind of useful way of understanding end behavior is you can test numbers. So for example, if we wanted to kind of play around with this idea, we could plug in a number like f of negative 100. Right? And so what would f of negative 100 be? It would be negative 100 squared, which is going to be, I always forget, it's 4 zeros, so that's 10,000. Right? So we can see that when we plug in a negative small number, we get a large positive number. And then same thing happens if we plug in a big positive number, like 100, well, we get the exact same result actually. So basically, because we're squaring a number, it doesn't matter whether it's negative or positive. That's the reason that both ends of the graph are pointing up. That's the reason that we have the same end behavior on both sides. And I'm going to erase this just because otherwise this graph will be, or this picture will be very cluttered. Okay, so next up we have f of x is, or g of x is equal to x cubed. So what does that graph look like? Well, we know it has a shape that's kind of like this. So we can see that something different is going on in terms of where these ends are pointing, right? And so in this case, as x approaches negative infinity, so what is going on as we plug in smaller and smaller x values? Well, the function is going down, right? And so we can say that g of x approaches negative infinity. And what about as we're plugging in bigger and bigger values? Well, in that case, the graph is going up. And so as x approaches positive infinity, g of x approaches positive infinity. So why is that, sorry, I keep writing the wrong thing. Why is that the case here? Like, what's different between these two functions? Well, it's because we're cubing, right? And so just to give a quick example, you know, to test this out, we could say g of negative 100. And so g of negative 100 would be negative 100 cubed. And so what happens when you cube a negative number? Well, it stays negative. So this would be negative, and then we'd have 6 zeros. So I guess negative 1,000,000. Whereas if we plugged in a positive number, positive 100, we would get a positive result. And so that's why this graph, one end points down and the other end points up. Okay, so next up we have just kind of the negatives of both of these. So this is h of x is equal to negative x squared. So what does that look like? Well, it's just it's been reflected over the x-axis, right? Negative x squared is just going to be an upside down parabola. So in this case, as x approaches negative infinity, we can see that the graph is going downward, and so we would say h of x also approaches negative infinity. And then on the right-hand side, as we're looking at plugging in bigger and bigger values, as x goes to the right, well, the function also goes down. So h of x also approaches negative infinity. And so why is that happening? Well, basically, when you square the input, you're always going to get something positive, right? So just to give a quick example, like let's look at this. So let's say that you were evaluating h of negative 100. Well, you would get negative 100 squared, right? And so what would happen is that the negative on the inside would go away and you would have 10,000, but then you have this extra negative sign on the outside that makes your result negative. And then the exact same thing would happen if you plug in positive 100, right? Because the negative sign on the inside, that was not the part that mattered. The part that mattered was this negative sign on the outside. And so regardless, you're going to get a negative number in both cases. All right, last up we have the negative x cubed. And so that one is going to be like the graph of x cubed, but flipped over the x-axis. So that's going to look like this. And so this one is going to have kind of the flipped end behavior of the one above it. So in this case, as x approaches negative infinity, where is the graph going? Well, k of x, this output, is going to be going towards positive infinity. And as x approaches positive infinity, well, the outputs are now going down. So k of x is going to approach negative infinity. So why is that happening? Well, it's basically because when you take a negative number and cube it, you get a negative result. But then we have another negative sign that's being applied, and so that flips it to positive. Whereas if you plug in a positive number, you get a positive result, but then you have a negative sign that flips it to negative. Okay, so we have these 4 different functions, and basically, if you know what the shapes of these 4 functions are, these are all of the different types of end behavior that are ever going to happen for any polynomial. So any polynomial, I'm not saying it's going to look exactly like these, but it's going to look something like one of these. It's going to have the same end behavior as one of these 4 graphs. So these are really the 4 graphs that you need to be familiar with. So for example, let's go back to the first example we did. So this was negative 2x to the 4th plus 3x squared plus 2x minus 1. So which of those general graph shapes does this match up with in terms of the end behavior, you know, the way that the ends are pointing? Well, it looks like the graph of negative x squared, right? Negative x squared was the one that went down on both sides. So why is that? Like, what is it about negative x squared that makes it similar to negative 2x to the 4th plus 3x squared plus 2x minus 1? Well, it turns out that the important part when you're finding the end behavior is the degree and the leading coefficient. So I'll write this down in a moment, but what I want to point out here is that in the case of negative x squared, this is an example that has an even degree, right? The degree is 2, and it has a negative, I'm just going to use LC to abbreviate leading coefficient. So we'll write this down, but it turns out that actually any polynomial that has an even degree and a negative leading coefficient, I'm not saying it's going to look just like this, but it will have a very similar shape. It will point down on both ends. And then what about this one? Well, this one was 3x to the 5th minus 2x squared plus 1. This one looks most like the graph of x cubed, right? And so why is that? It's because we had an odd degree and a positive leading coefficient. So this one is an example of a function that has, and I thought I left enough space here, but I guess I didn't quite. So let me just scooch this up a tiny bit. So this is an example of one that has an odd degree and a negative leading coefficient. Or sorry, positive leading coefficient. I feel like I keep making mistakes in this video. Right? And so what are these other ones? Well, this is what the graph will look like if we have an even degree and a positive leading coefficient. And then finally, this 4th one is what our graph will look like if we have an odd degree and a negative leading coefficient. So again, I'm going to summarize these rules in a second, but I just want to kind of point out, like, why does this happen? So why is it that when you have a function like this, so let's go back to our first example. This is like a complicated function, right? It has this, this part here where we have the negative leading coefficient and the even degree, but we also have all this other stuff there. So why do we only have to look at the leading term, basically? Why is it that the leading term dictates everything else? So it's basically because whatever is your highest power of x is just going to contribute a lot more to your output. So I want to kind of talk about that below here. So why does the leading term determine the end behavior? And when I'm saying leading term, it's because really we're looking at the leading coefficient and the degree, right? So together we can describe both of those by saying the leading term. Well, let's see what happens if we were to plug in a, let's start with a very negative number, right? So if we were to do f of negative 100, let's see what that would look like. So that would be negative 2 times negative 100 to the 4th. plus 3 times negative 100 squared plus 2 times negative 100 minus 1. And so I'm going to expand these out just so we can see kind of what's going on here. So this first one would be negative 2, and I'm not going to know how to pronounce this number out loud right away, but it's going to have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So that looks like it's 200 million. And then what about this next part? Well, this next part would be 3 times 100 squared. So that would be 3 with 4 zeros. So 30,000. This next part would be minus 200, and this would be minus 1. So what's going on here is that even though, these are big numbers, right? These are not insignificant. However, this number has so many more zeros than the rest of it that it's really this part that's going to control the outcome. And so if you add all of these up, you should get, if I did this correctly, negative 199,970, 201. So basically what we can see is that we get a very, very negative result, right? And that matches up with the end behavior. We said that as x approaches negative infinity, f of x should approach negative infinity. But my point here is that it's really enough to decide what the end behavior is going to be. It really is enough just to focus on the degree and the leading coefficient, because the leading term is just going to have so many more zeros that it's, especially when you're plugging in a really big number or a really small number. Imagine if we plugged in negative 1,000 or negative 1,000,000. This would have so many more zeros than everything else that really this stuff almost just doesn't matter. And the more and more negative of the number we plug in, the less and less that part is going to matter. And so similarly, if we plugged in positive 100, just write this one out quickly, that would be negative 2 times 100 to the 4th plus 3 times 100 squared plus 2 times 100 minus 1. I won't write out all the details, but for this one, you would get negative 199, 969,801. And so notice that this one, the result is a little bit different, right? We're not getting the exact same output, but they're pretty close, right? Considering that one number we're plugging in is negative 100, one is positive 100. And that just really goes to show that, again, it's really focusing on this part that tells you the general trend of what your function is going to look like. Okay, so let's go back here, and I just want to kind of summarize what we've discussed. So let me just make sure I'm getting my color coding right. So I'm going to start with purple. So for any polynomial, let me write this down, that the end behavior of any polynomial is the same as one of the 4 functions above. So specifically, if you have a polynomial that has an even degree, and a positive coefficient, leading coefficient, that tells you that it has the same end behavior as f of x is equal to x squared. Instead, if it has a odd degree and a positive leading coefficient, that means it has the same end behavior as g of x is equal to x cubed. Next one we had was negative x squared, and so that's the shape that you're going to have if you have an even degree and a negative leading coefficient, that's going to give you the same end behavior as h of x is equal to negative x squared. And then finally, if you have an odd degree and a negative leading coefficient, that's going to give you the same end behavior as k of x is equal to negative x cubed. And so basically what this is saying is that just by knowing the degree and the leading coefficient, it's not going to tell you exactly what the graph looks like, but it is going to give you an idea of the general shape. So now that we know all of this, I just want to do two more quick examples where without looking at the graph, we're going to figure out what the end behavior is. So we're going to describe the end behavior of the following two functions. So we'll do f of x is equal to negative 5x to the fifth plus 2x cubed minus x squared plus 2. And then we'll also do g of x is equal to 3x to the sixth minus 10x cubed plus 5x squared minus 7x. So let's start with the first one. So the first one, f of x, what is our degree? Well, the degree is equal to 5. And so 5 is an odd number. So that's the important thing to remember, is that we have an odd degree. And then what is the leading coefficient? Well, it's negative 5. And so what's the important thing to know about that? It's the fact that it's negative. And so what does this together tell us? This tells us that it will have the same end behavior as f of x is equal to negative x cubed, right? It's going to have that negative leading coefficient, odd degree. And so what I like to do is just draw a quick sketch of what that looks like, and then you can write down the end behavior from there. So what does negative x cubed look like? It looks like this. And so that tells us that as x approaches negative infinity, f of x is going to approach positive infinity. And then as x approaches positive infinity, f of x is going to approach negative infinity. So that would be our answer. So let's take a quick peek at what this function actually looks like. So we'll see that it does not actually look exactly like what I sketched here, but we'll see that it does have that same end behavior. So here's the function. We can see the middle has some different stuff going on, but we can see that, yeah, the left side is going up and the right side is going down. And that's exactly what we expected based on the end behavior that we identified. All right, let's do the next one. So for g of x, what is the degree? Well, the degree in this case is 6. So for g of x, the degree is equal to 6. And so remember, what we need to focus on is the fact that that's an even number. And then what is the leading coefficient? Well, the leading coefficient is 3. And what do we care about with the leading coefficient? Well, we care about whether it's positive or negative. So the important thing is here is that it's positive. And so because we have an even degree and a positive leading coefficient, that tells us that the end behavior, instead of looking like f of x is equal to negative x cubed, in this case, we're going to have the same end behavior as f of x is equal to x squared. And so our shape of our graph is going to look something like this. You know, it's not going to be a perfect parabola, but it is going to have that shape. And so that tells us that as x approaches negative infinity, f of x approaches positive infinity, right? It goes upward on both ends. And as x approaches positive infinity, and I guess our function, sorry, it was called g of x. So let me just fix that. G of x is also going to approach positive infinity. So let's check out this graph as well, just to confirm that we see that end behavior. Oops. So here is the function. Again, we can see that it doesn't look just like a parabola, but it does have that same general shape, right? We can see that the two ends to the right and the left are both pointing upward. All right, so that is it for this video. In the next video, we'll be talking more about polynomials. We'll be focusing more on finding the x-intercepts, and that's actually going to be kind of the main topic for the rest of polynomials is focusing on finding their x-intercepts. All right, I will see you all in our next video.